Section 3.8, Inverses and Radicals. This is our last section for this chapter. The first half should sound a lot like review for when we learned about inverse functions. To begin, let's find the inverse of polynomial functions. Two functions f and g are inverse functions if for every coordinate pair f, a, b, there exists a corresponding coordinate pair in the inverse function g, ba. Notice how b and a are switched. In other words, the coordinate pairs of inverse functions have the input and outputs interchanged. Verifying two functions are inverses of one another. Two functions f or g are inverses of one another if for all x in the domain for f and g, f of g of f of x equals x and f of g of x equals x, meaning composition of each other equal x. And you've seen this, and yet this is actually a homework test problem. Example 1. Show that f of x equals 1 over x plus 1, and f inverse of x, which equals 1 over x minus 1, are inverses. Well, according to our definition, if one of them is f of x and we label the other one g of x, then if I compose them, then my answer should be x. So all it comes down is, does composition result in x? Let's find out. So composition means we're going to take this function and I'm going to plug it in for every x in the other function, so just there. So that we have 1 over, and instead of x, I'm going to write 1 over x minus 1, and then all plus 1. Okay, since we're adding, we can just drop the parentheses. So I have 1 over x minus x plus, minus 1 plus 1. We see the minus 1 and plus 1, add to make 0, and we're left with 1 over x. Well, that's just division. So would it make more sense if I write it 1 divided by 1 over x? Well, that would give us 1 times. Remember, you keep change flip, so you keep the first number, change to multiplication, and flip the reciprocal. So I have x over 1. You multiply across, and we just get x. So yes, they are inverses. All right, next example is asking to find the inverse. We've done this maybe, I want to say maybe 3 or 4 sections ago. I think it was last chapter, it was in chapter 2. So to find the inverse, let me help you recall the steps. You want to first change f of x to y, and then you want to swap your x's and y's, so you want to interchange x and y. 3, you want to solve for x. 4th, change that f of x to, or change y to inverse function notation. And there you have it. So let's go ahead and follow our steps. So first I want to change f of x to y. So I have y equals 5x cubed plus 1. Then I want to swap them. So that I have x equals to 5y cubed plus 1. And then I want to solve. I wrote x, I meant to write y. Then you want to solve for y. So you want to get y by itself. So I subtract 1, we're left with x minus 1 equals 5y cubed. Want to get y by itself, so let's divide by 5, and we're left with x minus 1 over 5 is equal to y cubed. All right, to undo that cubic, I want to apply the cube root, because that exponent of 3 and that radical of 3 are mathematical inverses, so they undo each other. So that we're just left with y is equal to the cube root of x minus 1 over 5. Last step, you want to go ahead and change that y to inverse notation so that I have f inverse of x is equal to the cube root of x minus 1 over 3. And there we have it. We found the inverse of the function. Now we have to consider restricting the domain because for some functions that are not one-to-one, they have their domain restricted so that they are one-to-one, but only after that domain has been rearranged. The function over the restricted domain would then have an inverse function. Since the quadratic functions are not one-to-one, we must restrict their domain in order to find their inverses. So it starts off with the example of a quadratic. So to remind you what that graph looks like is quadratic is a U-shaped function. Okay, and it fails to be a function, a one-to-one function, because it fails that horizontal line test. It crosses that line twice. But what if we restrict it? So we can restrict it from your positive x's, and we can restrict it to only consider your negative x's. So from the left and the right. If we only have positive x's, then our graph would look like this. If we only have negative x's, then our graph would look like this. So we can restrict our domain so we only have either the positive or the negative, for example. And if we do that, then it will not fail the horizontal line test. And if we do that, we will allow for an inverse. Let's talk more about restricting the domain. If a function is not one-to-one, it cannot have an inverse. If we restrict the domain of the function so that it becomes one-to-one, thus creating a new function, this function will have an inverse. All right, here we have an example. Find the inverse function of when x is greater than 4, of f of x equals x minus 4 squared when x is greater than 4. And then we have another one. F of x is equals to x minus 4 squared when x is less than 4. So let's go ahead and find the inverse. Now that we have restricted inverse, we should be okay. So let's start with our inverse rules so that I have y is equal to x minus 1 minus 4 squared. Okay, let's swap our x's and y's so that I have x is equal to y minus 4 squared. Let's take the square root of both so that that square and that square root are gone, and we're left with, now we have to consider plus or minus. Here is where that restriction comes along. Because we want those greater, we only want the positive, not the negative. So that I have positive square root of x is equal to y minus 4. Did you catch that? That's what we did with the domain restriction. Because if it had a positive and minus, then that would be the case where it's not one-to-one, and it would cause a problem. But since we only want the positive, we're fine. Okay, last bit. Let's go ahead and move 4 by adding 4. So then I'm left with the square root of x plus 4 is equal to y. Let's change y to inverse function. So we're left with the inverse of x is equal to the square root of x plus 4. And there we have an inverse function. Let's do the same thing, but now we want those that are less than. We want the negative option. So let's go ahead and find the inverse. Let's change that f of x to a y so that I have y is equal to x minus 4 squared. Let's swap our x's and y's so that I have x is equal to y minus 4 squared. Let's get y by itself. So let's undo that square by applying the square root. But because we want those that are less than, we want only the negative. So that I have a negative square root of x is equal to y minus 4. That square and square root are gone. let's move the 4 to get y by itself. So that we have 4 minus square root of x is equal to y. Let's change that y to inverse notation. F inverse of x is equal to 4 minus the square root of x. There we have it. Next example. Restrict the domain and find the inverse of f of x. So we have f of x is equal to x minus 2 squared minus 3. So let's consider our graph. Let's do a really rough sketch. So I have this graph and I have a vertex at 2, comma, negative 3. So I know we have that peak at 2, negative 3, and it opens up. So if I want to split it in half, so they only have the right and the left, we want those when x is greater or equal to 2, and those that are less than or equal to 2, because that 2 is that marker where it separates the left part of our parabola and it separates that right part of our parabola. So that vertex, we need that x of our vertex. Okay, so now we have two functions. Well, we want to restrict our domain to create two functions. So one of them will be f of x equals x minus 2 squared minus 3 when x is less than or equal to 2, just like we saw above. And our other one would be f of x is equal to, well, we have our function, nothing changes, but then our restriction, our domain is what changes. Now we want when x is greater than 2. So that we get our left part of our parabola, and so that we get our right part of our parabola. That's pretty cool stuff, right? One more. Restrict the domain of your function. No, it's restrict the domain and then find the inverse of the function. So here we're given a radical function. Now let's think about what this looks like. So this square root function, square root functions look like this, like a sideways half of a parabola. But since we have a shift to the right 4, our graph looks like this, at 4 and like that. We know we have a shift to the right 4 because of that minus 4. And yes, we see minus, so we want to think it goes to the left, but it goes to the right. Okay, so let's go ahead and find our inverse. Once we find our inverse, we can go ahead and restrict our function. So really, we didn't really need this. I kind of just got ahead of myself. Okay, so let's go ahead and find the inverse. Let's change f of x to y so that I have y equals the square root of x minus 4. We interchange x's and y's so that I have x is equal to the square root of y minus 4. Let's go ahead and solve for y. So I want to square that to undo that square root. So then, and when we do to one side, we do to the other. So I'm left with x squared is equal to y minus 4. Lastly, I want to get y by itself, so I add 4. And we're left with x squared plus 4 equals y. Now I want the inverse notation, so I have f inverse of x is equal to x squared plus 4. Okay, now we have this function, and this function is a parabola. Is a parabola that's shifted up 4. So here's what I have to consider my vertex. So this graph is up 4 and it opens up. Now, inverses also need to be 1 to 1. So I need to restrict my domain. Let's restrict our domain for those bigger than that. So we would say when, because we have this vertex at 0, 4, when x is greater or equal to 0. And that is our inverse function with a restricted domain. That's it for 3.8, inverses and radicals. Your homework is 13 through 31, every other odd.